Okay, so I'm just going to review the laws here. We looked at them in class the other day, and I'm just going to try and take a couple questions from each picture, or each chapter of the book. So this is the first bit of homework that I've asked you to do is in exercise 6a, and it's using this law where if you have two bases and you multiply them together, you add the indices. So remember, bases can be numbers or bases can be letters like so. So x squared times x cubed. So you have two possibilities with bases, okay? So if I have the same base, 3 squared times 3 cubed, you keep the same base and you add the exponent. So we have 3 to the power of 5. So it's a simplify using the exponent laws. And that's what we're going to do. And then in part B, if you look at this, we have once again the same basis. So I have 2, which I keep the base. Now I'm going to see a lot of people do this. Be careful. They're going to go 2 squared times q cubed, and they're going to say 4 to the power of 6. Never, ever multiply these two to get 4. That is not the rule. Okay? So if the same bases, we keep the same base and we add the exponents. So we have a 4 here. Okay? So that's the first piece in 6a. In the second number in 6a, we have a few questions here, but in this case, it's the division rule. So it says that if we have the same base, then we can subtract the indices. So let's take these two. I'll separate them here. Okay. And for example, I have 2 to the power of 4 and 2 to the power of 2. So it says that we keep the same base, so 2, and we subtract the top indice, which is 4, subtract the bottom's indice, which is 2. And then we end up getting with 4 squared. Okay. If we do it with x's, notice that there's a same base, x and x. So what we're going to have is we keep the base, and we once again subtract the top exponent, 6, minus the bottom exponent. And this gives us x to the power of 4. Okay, so we have that. And here on the third one, notice that there's no exponent on that number 3 here, but there is. Everyone should realize there's a hidden 1. So if it helps you, rewrite it so you have it like this, and then apply the rule which says keep the same base again, but subtract the top exponent minus the bottom exponent. If this is the case, we have 3 squared. Okay, so we have that here for this law of the division of the same base. Next, we have this other law which says if you have some number to the power of some, or a base to the power of some number with another number on the outside of the brackets, you can bring it in here and they multiply. So this is multiplied. Okay. So we make sure we have to multiply. So for instance, let's just take an example that we have here. If I use a, well, according to this rule, we keep 2 the same, and I'm going to multiply 2 times 3. So this is 6. Okay. Now be careful, because I know what people are going to try and do. They're going to get mixed up, and they're going to say 2 plus 3 is 5, which is not the rule. There's no adding exponents when we have them on the outside here. It's multiplying. So make sure you really understand your rules. I'll do another example. This time I'm going to do it with p. So we keep p the same, and I bring 3 and I multiply it by the other 3, so we have p to the power of 9. Okay, so that's the simple rule here where you bring the number in. Okay, let's take a look at the next one. So this one's a little bit similar than the previous one, except for instead of having, for example, a to the power of something here to another power, we have 2 separate algebraic letters to the power of 1 power n. And it says there you have to bring the n into both the a and the b. So another way of looking at it is you have a to the power of 1, b to the power of 1, because we know that there's hidden 1s, and on the outside there is n. And what we want to do with this is take this n and multiply it by 1 and multiply it by 1. But this is not always the case. This could be a 2 or a 3, so we really have to make sure that whatever this number is on the outside, we multiply it by every exponent on the inside. So let's take a look at one of our examples. Bring this over here. Okay, so in this case we have 2 and we have a squared. So we have to bring the 2 in to both of them. So remember there's a hidden 1 on this 2. So what we're going to have is 2 to the power of, well, 2 times the hidden 1 is 2. And then 2 times the 2 in the a is a to the power of 4. So there we go. And now you can simplify this a little bit more. 2 squared is like saying 4 a to the power of 4. Okay. Let's try a second one just to make sure we understand. Okay. So we have our j, there's a hidden 1 there. So we're going to have the 2 and he's going to come in and multiply that hidden 1. So we have j squared, 2 times 1 is 2. And then this 2 is also going to come in and multiply the 3. So you have k, 2 times 3 is 6. And actually, if you'd like, just to make sure we understand the rule, we can extend this so that I have a really big number or really big algebraic term, say 3a squared b cubed c to the power of 4 and d to the power of 5. So imagine we have this, and on the outside, let's put a 3. What we're going to do is, the more of these terms we have to make sure the 3 comes in here and multiplies every single one of them, every exponent. Okay, you have to distribute this 3, and of course there's a hidden 1 here. So in this example, if we did it, we'd have 3 to the power of, well, 3 times 1 is 3. A to the power of 3 times 2 is 6. B to the power of 3 times 3 is 9, so we have B9. C, 4 times 3 is 12. And finally, we have 5 times 3, which is 15. So there you go. So here it doesn't stop just with 1, 2, or 3. You have to do it to everyone. So notice in some of the years there's a 3, there's an H and a K. You have to bring the 3 in everywhere. Okay? Not just 2 of them. Bring it in and multiply it. And make sure you put your hidden 1s everywhere so you can multiply the 3 against the hidden 1s. All right? So that's this rule here. It's expanding this n into the brackets. Now here's a different rule that we have. And in this case, what we have is we have a and b, a fraction, and we have an exponent on the outside. And what we need to do is, once again, bring this n here into the a, but we should also bring it into the b here. So if I rewrite this up here, once again, I have a to the power of 1, b to the power of 1, or hidden 1s. And on the outside, we have n. So if I'm going to FOIL this in, it's going to be n times 1, or whatever power is on a, and n times 1, or whatever power is on b. So they don't necessarily have to be the hidden 1. Okay, so in this case, it's very simple. You bring the 2 times the hidden 1, and you bring the 2 in again times the hidden 1. So you end up getting a squared over b squared. Okay, let's try maybe a more difficult one here. So let's grab this one here. And now what happens is, if you look, I have a j, a k, and a 2. So just like the previous one, I need to bring the 2 into the j and the k, but because there's division, I can bring it into the 2 as well. So I'm going to rewrite this so you can see it better. So j to the power of 1, k to the power of 1, and 2 to the power of 1. And all this is to the power of this outside 2. He's going to come in here and multiply the 1 there, so we're going to get k squared. Going to come in here and multiply the 1 on the j, so we have j to the power of 2. And he's going to come in and multiply this 1 here, so we have 2 to the power of 2. And of course, you can simplify this a bit. It'll be j squared, k squared over 4. All right. So there's that rule for you as well. Okay. Of course, if I have something like this, p to the power of 3 over q to the power of 4, and all this is to the power of 5, well, we no longer have our hidden 1, do we? So we just have to go 5 times 3, which is p to the power of 15, over 5 times 4, which means it's q to the power of 20. So that's how you would do it if there's no exponent on these numbers, right? There's always a hidden 1, but in this case, now we have a 3 and a 4, so we multiply them. In exercise C, this is the zero index law, which is the easiest out of all of them, because if I have anything, no matter what this is, to the power of 0, that's equal to 1. So if we look at some of the examples, they're straightforward. We have 7 to the power of 0, 1. 8 plus 10 to the power of 0, which is 1, so that gives us 9. And once again, we have 2 to the power of 3. And if you do that on your calculator in your head, you're going to get 8. And from there to the power of 0, we also get 1. All right, so that rule is fairly straightforward. You just have to make sure that you make anything to the power of 0 equal to 1, and anything else, you don't have to worry about that, okay? So even negative numbers, negative 3 to the power of 0 is 1. A fraction, 4 over 5 to the power of 0 is equal to 1. All right. And now if we look at the last rule here, this is one that confuses most students, but it's quite simple. I explained it the other day. It's with the negative indices. So if you have, say, 5 to the power of negative 1, this 5 to the power of negative 1 has a denominator which is a hidden 1. And if I like to, the rule says that I'm allowed to move this 5 beside this 1. So imagine I have the 1 still there, and now I've put the 5 beside him, but this indice changes sign. So if it's negative, it becomes positive. Now the big question is, what is left on top? Some people will say 0, but that doesn't make any sense, because then you'd have 0 divided by this is 0. So remember, there's always a hidden 1 in front of that, so you left with the hidden 1. All right? So what you end up with is 1 over 5 to the power of 1, which is 1 over 5. Okay? And of course, you can look at the same thing here. 4 to the minus 1 using the same idea is 1 over 4 to the power of 1. So those are most of the rules that I tried to explain to you in class the other day. As you get into the questions, they're going to be more and more difficult. So I can give you an example of something a little bit more difficult if you want to try and be challenged. I did assign it. So let's try, for example, something like this one here. And if you see, we have this 3g to the power of 2 times 2g. So what it's done is it's combined these indice laws. So remember, we have this to the power of 2. We have to bring it into both of them. So if I have my hidden 1, I have 3. I bring the 2 in and times it by the hidden 1, so that's 2. And g also has a hidden 1, so I have 2 times 1 there, and I have g squared. So if I do that, another way of thinking about it is going 3g to the power of 2 is like saying 3g times 3g. Of course, 3 times 3 is 9, which you get here, and g times g is g squared. So that's another way of looking at it. So here we have this bit here from the first bit, but that's also multiplying 2g, so we have to do the next bit as well. So now what I'm going to do is I'm going to simplify 3 squared into 9g squared times 2g. And what I'm going to do is multiply the numbers. So 9 times 2 is 18. And what's g squared times g to the power of 1? Well, we know that when you have the same base, g times g, and you have the same base, then you have to add the exponent. So 1 plus 1 is 2. So if I have 2 here and 1 here, I should get 2 plus 1, which is 3. So there is more advanced one for you, okay? And then even more advanced are these ones where you have to have division at the same time. So I'll do the last one just in case someone gets through them and wants to try something very difficult. I'm going to rewrite it so it's bigger. 5g over 2h cubed. I'm going to add my hidden ones here, here, and here. So those are my hidden ones. And all this is to the power of 3. So we have this rule that says if I have a over b to the power of some number here, I have to bring in this power into both of them. But look how many I have. I have 1, 2, 3, 4. So what I'm going to do is I'm going to go 3 times 1. So I get g cubed. 3 times 1, which is 5 cubed, all over 3 times 3, which is h to the power of 9, and 3 times 1, which is 2 to the power of 3. And then you can simplify it a bit. So 5 cubed, if you do it on your calculator, you should get 125, and you have g cubed here. And if you do 2 cubed on your calculator, you should have 8. And of course, you have h to the power of 9, which we got by going 3 times 3. So this is your final answer for that question there. So try to attempt as many as you can. I'm going to check Shobi to see if you have finished them for the classroom.